Picture the familiar night sky, calm and patient, like a library at closing time. Now imagine the doors swing open and travelers start tiptoeing through the stacks, leaving footprints of light across the aisles. That is the mood shift we are stepping into. For most of human history, the heavens were a stately backdrop. Nothing rushed, and nothing from beyond our neighborhood dropped by for tea. Then along comes an object labeled 3I/Atlas, a visitor from elsewhere, and suddenly the wallpaper moved. The universe tapped the glass and whispered, "You have mail. Good evening, curious minds." Science doesn't need to shout to be fascinating. Sometimes it's best enjoyed the way you'd enjoy a late-night conversation, quietly, with a cup of tea, and maybe the soft hum of a fan in the background. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing. No pressure, only if you enjoy these calm journeys through the universe. Now, let's begin. What makes this moment feel different is not just the novelty of a foreign rock paying a visit, it is the implication that space is livelier than we thought. The cosmos is less like a quiet cul-de-sac and more like a city corner, where the light never turns red. If one traveler found its way here, the odds tilt toward many more. Think of our solar system as a cafe near a busy station. We thought we were the only regulars. Turns out, there is a steady trickle of folks rushing in for a brief espresso, dropping a few crumbs of story, then hurrying on. Let us set expectations. We are not talking about giant star cruisers with neon signs. These are small, natural bodies, more pebble than planet, but they carry something priceless: context. A visitor, like 3I/Atlas, is a messenger that does not speak in sentences. It speaks in ingredients. It brings the dust of a distant nursery, the frost of another sun's winter, the mineral scars of collisions that happened before our oceans were fully settled. It is like receiving a postcard that smells faintly of an unfamiliar sea. You cannot read the whole story, but the scent tells you the beach was real. The psychological shift is fascinating. For centuries, humans have pointed outward with a leave-the-nest energy. Build rockets, leave footprints on new ground, plant flags, send probes with golden records that say, "Hello" from the chatty primates on the third rock. The arrival of interstellar visitors flips the script. Instead of us leaving home, home is on a route that others naturally pass. The front porch is part of a wider footpath. Suddenly, hosting becomes as important as traveling. We need new manners for meeting the unknown. Shake hands, but wear gloves. Offer tea, but label the sugar jar. Curiosity and caution can share a table without starting an argument. Culturally, this moment invites wonder with a side of practical to-do list. Wonder, because it reframes our address. We live in a system that is not isolated. Practical, because we should be ready to notice, ready to listen, and ready to learn without making a mess. The first step is paying attention. The night sky used to be a screen we admired. Now it is a notification panel. The vibe is less still life, more slow news ticker. The headline is simple: guests are possible and possibly frequent. The subhead says, "Prepare your questions." Here is a soft truth that sneaks up on you. Our sense of belonging expands when the unfamiliar shows up at our door. It means our story is woven into a larger fabric. When a traveler from another stellar street rushes past, it brings evidence that our galaxy is not a set of sealed apartments. There are drafts under the doors and letters slipping through the slots. That changes how we think about our place. Earth is basically a rock that won the cosmic lottery. And the jackpot is not just life. It is membership in a grand, slightly messy neighborhood. There is also the thrill of narrative. Each new visitor is a character entrance. Just a silhouette at first, then a reveal of shape, color, maybe a hint of attitude. Some will be shy and dark, others glittery and loud under the sun. They will not stay long, and that is part of the drama. We get a brief window to say, who are you? Where have you been? What are you made of? And what stories do you carry in your dust? The questions are simple. The answers are deliciously complicated. That is the heart of good science and good storytelling. Short questions, long echoes. Humor helps us hold the awe without dropping it. Photosynthesis is plants' way of saying they invented solar panels first. These visitors are the universe's way of saying it invented the surprise party. Black holes are the universe's way of saying delete browsing history permanently. Passing interstellar rocks are the universe's way of leaving a mysterious text at 2 in the morning that just says, outside. We can laugh while we take notes. Wit does not cancel rigor. It clears room for it. If this is our new normal, it asks for a new rhythm. A rhythm of paying attention without panic, a rhythm of asking generous questions and setting careful boundaries. Think of the planet as a museum with a lively lobby. Guests may pass through the foyer. We decide which rooms to open, which doors to keep closed, and how to guide the tour so everyone leaves wiser than they arrived. The stakes are not about drama. They are about maturity. Can we be curious hosts, thoughtful and prepared, who learn quickly and share fairly? Above all, this chapter sets the tone. The sky is not a static dome, but a living river. Things drift in, things drift out. And in that flow are clues to our wider family history. If 3I/Atlas is a first hello, then the smart move is to say hello back with care, humor, and a notebook, because somewhere in that faint smudge is a sentence that changes how we think about where we came from and where we might go next. Stay with this energy as we step forward. In the next chapter, we will trace how such travelers find our doorstep at all, following the soft currents of gravity and time that guide them like unmarked roads on a galactic map. After that, we will learn how to spot the next faint stranger before it slips past the cafe without ordering. Chapter 2. Why They Come Here, Galactic Highways and Gravitational Gates. Imagine the galaxy as a vast ocean, with currents you cannot see, but ships follow anyway. Interstellar visitors are those ships, and their captains are not conscious minds, but gravity itself. To understand why something like 3I/Atlas shows up, we have to map the hidden lanes, the long pull of the galactic tide, the chance nudge of passing stars, and the slingshot tricks that fling debris from their home systems into the wide dark. Think of it as celestial traffic engineering, with detours, on-ramps, and one very patient speed limit set by physics. Start at the birthplace. When a star and its planets form, they do not tidy up. A young system is a messy construction site with leftover bricks. Those leftover bricks are planetesimals, ice-rich kernels, rocky shards, and everything in between. Giant planets act like bouncers with bad aim. When a fragment wanders too close, the giant planet does not simply swallow it. More often, it gives the shard a wild redirect. Each shove can lift the fragment into a stretched orbit, and repeated encounters tighten the spring until the object is launched clear of its original sun. Congratulations, you have an interstellar traveler. Space is a strict teacher. If you do not fit in the schedule, you are expelled. Clusters make the expulsions easier. Many stars are born shoulder to shoulder, like infants in a crowded nursery. In that early era, stars pass within respectable but influential distances of one another. A close approach is not a collision. It is a handshake that rearranges pockets. Comet clouds are stirred, outer planets tugged, and the odds of ejecting debris spike. A single flyby can turn thousands of sleepy, distant objects into wanderers with one foot already out the door. If a young system is a neighborhood soccer game, a passing star is the gust of wind that sends the ball into the next street. Now zoom out to the galaxy's slow tidal breath. As our entire solar system orbits the galactic center, the collective pull of the Milky Way gently tugs on distant reservoirs of small bodies, far from any sun, where an object barely belongs. Even a soft tug matters. Over millions of years, the galactic tide stretches orbits, loosening the hold of home stars on their coldest citizens. Some drift inward toward their own suns and become comets. Others drift the other way and slip free like a kite string that quietly breaks. The process is not dramatic. It is persistence wearing down loyalty. Between these broad tides and local flybys lies the city's favorite trick, the slingshot. Gravitational assists are not just for spacecraft. Natural bodies pick up or lose speed by sailing close to massive objects. A shard that skims a giant planet can be hurled sunward or skyward, trading direction for energy. If the exit line points outward with enough speed, the fragment becomes a message in a bottle launched from the beach of one system into the surf of the galaxy. It travels for ages, not because it is determined, but because nothing says stop. All of these pathways create wanderers, but why do some of them end up near us? Here is the intriguing part. The galaxy is not uniform. It has spiral structure, moving groups, and regions where relative motions cancel, just enough to form what sailors would call a calm. Our solar system drifts through the disk with its own speed and direction. If there is a patch where our motion almost matches the average flow of local debris, then to us, the traffic looks slower, like walking along a moving walkway that nearly keeps pace. That would create a slow lane, not in the sense that objects go leisurely, but in the sense that the difference between their path and ours is small. Smaller differences mean longer encounter times and higher chances of discovery. Picture leaves circling a storm drain. The water does not yank every leaf straight down. Many hover in lazy spirals near the grate. In this analogy, the grate is our region of space. We are not a trap, but we might be a place where trajectories cross gently, giving us more than our fair share of fleeting company. If this slow lane idea holds, it could explain why we might detect not just a single passerby, but a sequence, each from a different birthplace, all wandering through the same corridor we happen to occupy right now. Cosmic timing is a talent we did not know we had. There is also the effect of stochastic scatter, which is a fancy way of saying chance encounters build structure. Over long timescales, fragments are nudged by a soup of small forces, distant stars, giant molecular clouds, and gravitational echoes from spiral arms that orbit the galactic center like slow waves on a pond. These ripples can herd debris into streams. Astronomers already see stellar streams made from disrupted clusters and dwarf galaxies. Why not smaller, fainter rivers of rock and ice, too subtle to map directly, yet real enough to send the occasional pebble our way? If star streams are the highways, these debris rivers are the frontage roads, now fold in the role of time. Travelers that left their homes when dinosaurs wandered our continents are still out there. Ages do not erase them, they only round the corners and bake the surfaces. Radiation toughens the skin, spin states jitter from tiny thermal effects, and volatile ices retreat into sheltered pockets like campers huddling from wind. By the time such an object drifts near our sun, it is a veteran. It will not tell us everything about its birthplace, but it will tell us something, the way a suitcase always carries a hint of the last hotel. Here is the speculative twist that turns the head. What if our solar system's current path places us at the edge of a gentle resonance between local rotation and spiral arm pattern speed? In plain speech, what if we are cruising beside a slow wave in the galactic disk, where relative motions are a little calmer? For a few million years, that could raise the likelihood that free-floating shards wander through our zip code. Not forever, not by design, just long enough for curious primates with telescopes to notice a pattern and feel very lucky to be awake for it. Space loves long stories. Sometimes we walk in during the interesting chapter. The result is not fate or fortune-telling. It is the honest, quietly dramatic flow of gravity, writing in very slow cursive. Interstellar visitors come here because the galaxy gives them ways to be born, ways to be flung outward, and lanes that, for a while, run beside our door. They are not seeking us, they are simply moving, and for a brief slice of time, our address lines up with the traffic. If we are wise, we will step to the railing, watch them pass, and keep a net ready for the rare one that drifts within reach. Chapter 3. Eyes on the Sky. the detection revolution. Imagine a newsroom that never sleeps, where the breaking story is a single pixel that moves between two frames. That is modern sky watching. The quiet romance of one astronomer at a lonely dome still exists, but the main act now is a symphony of survey telescopes, wide-field cameras, and patient computers that never blink. The goal is simple to say and wildly hard to do. Catch faint strangers racing through a giant volume of darkness, and do it fast enough that the world can react before the guest has already waved goodbye. It is cosmic paparazzi, except the celebrities do not sign autographs. They reflect sunlight and try to escape. Start with the cameras. Old-school astronomy prized narrow, deep looks at small patches of sky. Today's discovery machines flip that idea. They paint huge swaths at once, trading extreme depth for breathtaking coverage. Think of them as street sweepers that glide down every avenue, making sure nothing is left unnoticed. Wide-field optics feed arrays of detectors that act like tiled retinas, each chip collecting a slice of the sky. In a single night, they can gather more images than entire observatories once gathered in a season. Earth is basically a rock that won the cosmic lottery. These cameras are the eyes that cash the ticket. Coverage is only half the story. Cadence is the heartbeat. To catch a mover, you must look again, and then look once more, with precise timing. The telescope returns to the same field minutes later, hours later, nights later, building a rhythm that turns still images into motion. If a pixel slides between frames, that is a clue. If it slides in a straight line with a consistent pace, that is a stronger clue. Cadence is choreography. It teaches the software the difference between noise that flickers and an object that travels. Think of it as the drumline that keeps the whole band in step. Enter the pipeline, the hidden factory, where raw images become actionable news. First, every frame is cleaned of cosmetic distractions, dead pixels, faint ghosts, and the occasional glint from a satellite that photobombs the view like a tourist with a shiny watch. Then comes differencing. The computer subtracts a reference image from the new image, leaving behind what changed. Most changes are imposters, a sensor hiccup, a cosmic ray zap, a bright variable star doing star things. But sometimes the subtraction leaves a neat little dot that shifts between exposures like a shy dancer. That is the kind of dot that makes astronomers sit up straight. Machine learning is the new bouncer at this crowded club. It has seen thousands of fakes and a growing library of the real deal, trained on vast datasets. It learns to tell a true moving object from a smudge with remarkable speed. The program does not care about romance or myth. It cares about shapes, intensities, and trajectories. It triages candidates, elevating the most promising to the human eye, and binning the rest with unceremonious efficiency. If the universe is a prankster, machine learning is the straight-faced friend who says, "Nice try, now show me the real clue." Automation turns discovery into a relay race. Once the software flags a target, an alert fires off to networks of telescopes around the world. Robotic mounts swing to new coordinates, while most of us are brushing our teeth. Smaller instruments take follow-up images to confirm motion. A few larger telescopes grab early spectra to sniff out what kind of surface we are seeing. Within hours, a candidate can graduate from anonymous dot to tracked object, with a provisional orbit. It is the difference between a rumor and a headline. The magic multiplies when the community steps in. Picture a weather app, but for comets and fast movers. A push notification says, "Bright visitor near the southern horizon before dawn. Best viewed with binoculars." Amateur observers, schools, and backyard astronomers respond in minutes, uploading images and timing data. Their observations, properly calibrated, fold into the professional pipeline. This is the what-if twist that matters. What if comet tracking becomes as routine as checking tomorrow's rain chats? Imagine a world where a teacher starts homeroom with, "Quick update. The visitor is now 3 degrees east of that bright star, and here is a fresh frame from my phone connected to the school scope." This democratization does not cheapen the science. It supercharges it. More eyes mean more time zones covered, more weather gaps filled, and more chances to catch a brief outburst or a sudden change in spin. The data flow becomes a river with many tributaries, all feeding a shared map that updates in nearly real time. And because the pipeline is built to handle floods, it digests the surge without choking. Photosynthesis is plants' way of saying they invented solar panels first. This network is humanity's way of saying we invented Curiosity Cloud services. Behind the scenes, careful standards keep the party tidy. Timestamps are synchronized to a shared clock. Coordinates are checked against star catalogs, and uncertainties are reported, not hidden. The system knows that a fast false positive can waste precious hours. It also knows that a slow true positive can cost a discovery. So it errs on the side of quick humility. Flag early, confirm quickly, revise often. The motto is not perfection, it is progress with receipts. What about the sheer volume of noise from our own technology? The sky is busy with satellites, and they love to leave bright streaks like uninvited graffiti. New algorithms learn to predict and mask those paths, while observatories coordinate with satellite operators to plan around the worst moments. It is not perfect, but it is improving, and the software keeps learning. If black holes are the universe's way of saying delete browsing history permanently, these filters are the sky's way of saying please do not tag the mural. The end result is a shift in tempo. Discoveries that once took months now take nights. A faint streak becomes a headline before breakfast, and a target of opportunity can trigger follow-up from an entire hemisphere. The story is no longer captured by one hero at one telescope. It is written by an orchestra of lenses, servers, and humans who agree to share. The sky has not changed its mind about being large and dark. We changed our strategy for listening. In this new era, a moving pixel is not a curiosity. It is a doorbell. We can answer promptly, invite the guest into our field of view, and take the first careful measurements that begin the longer conversation. The next chapter will lean into that conversation, showing how the very first minutes after detection become a crisp playbook for classifying what kind of traveler we are meeting and how to greet it without missing a beat. Chapter 4, The First 10 Minutes. Rapid Classification Playbook. There is a very specific kind of adrenaline that arrives when a fresh alert pops up before the kettle boils. It is the astronomy version of hearing the doorbell while you are still in slippers. The goal of the first 10 minutes is simple to say and tricky to execute. Figure out what this thing is, or at least what it is not, before it slips behind the curtains of daylight or geometry. Those minutes are a sprint filled with quick measurements that do not sacrifice care. Think triage nurse with a stethoscope and a calm voice. Minute 0, the ping. An automated notice lands in the queue with a sky position, a timestamp, and a small note about apparent motion. That motion line is the opening chord. Objects that drift across the star field faster than usual deserve a closer listen. A scheduler grabs nearby telescopes that are awake and points them slightly ahead of the target, the way you lead a runner before you toss a ball. The first job is to nail the path on the sky with precision, because a good path lets everything else line up. Minute 1 to 3. Astrometry, which is a fancy way of saying pinpointing location against a star grid. Several short exposures track the object, while the telescope follows its movement rather than the stars. This keeps the visitor sharp and turns the stars into tiny streaks. The software measures the center of that moving dot again and again, then fits a simple path through those measurements. The path tells us the rate and direction on the sky, and when combined with the exact time and the observatory's position on Earth, it starts whispering clues about distance. No equations on screen, just a quiet confidence. This thing is here, and it is moving like so. Minute 4, shape and sharpness. A quick look at the light profile shows whether the object is a clean point or a fuzzy smear. A growing blur can mean evaporating ices, which is comet speak for I am warming up. But blur can also be a trick of speed. So the pipeline corrects for trailing to avoid misreading a fast rock as a fluffy snowball if the visitor is still point-like after that correction. The working label leans away from active comet. If it shows a faint halo that grows between images, we keep the comet box open. Minute 5. Color snapshots. The telescope cycles through a set of filters, capturing how bright the object appears in redder light and bluer light. The difference between those brightnesses is a quick personality test. Some surfaces reflect blue light strongly, others tilt toward red, and that tilt often tracks with surface chemistry and grain size. A very red slope can hint at long exposure to space weathering, while a more neutral tone might say fresh crust or predominantly rocky makeup. It is not a biography, but it is a haircut and a jacket, which is more than nothing. Minute 6. The rate check. The team compares the observed drift to what a typical local body would show at that part of the sky. If the motion is suspiciously fast or heading the wrong way for the usual local families, ears perk up. Software does a lightning round of possible paths under the assumption the object is bound to our star. If every bound solution twists into an awkward pretzel, the unspoken thought appears, this could be an outsider. We do not declare it, we let the numbers say it by refusing to fit a comfortable loop. Minute 7 to 8. A rough spectrum, a small dispersing element, often a simple prism-like device, breaks the visitor's light into a soft rainbow. Even a blurred rainbow can whisper whether we are looking at rock sprinkling and metal-rich surfaces, ice-rich crust, or a mixture with complex organics. Lines from simple gases, like cyanogen or sodium, can pop up even at low detail if there is a bit of activity. The presence or absence of those lines in the very first look is a strong hint about behavior near the sun and helps decide whether to plan deeper chemistry later that night. Minute 9. Consistency check across instruments. A second telescope, sometimes on another continent, repeats the basics. Two viewpoints tighten the path dramatically. Parallax between observatories, even if small, sharpens the early distance estimate and strips away bad guesses. If both teams see the same color tilt and the same point-like shape, confidence grows that the early snapshot is telling the truth, not a lighting fluke. Minute 10. Provisional tags. With position, motion, color, and a first rainbow in hand, the coordinator assigns a temporary identity, likely asteroid, likely comet, or high-interest outsider. The outsider tag is not a victory lap. It is a call to arms. It tells bigger instruments to warm up and tells small ones to keep up the rhythm so that the orbit solution firms up hour by hour. Now for the interesting part. How do we tell an interstellar oddball from a local comet without waiting weeks? The early clues arrive as a bundle. If the path refuses to make peace with bound orbits under any reasonable assumption, that is one vote. If the object stays stubbornly point-like at distances where local comets usually sprout a faint haze, that is another. If the color slope looks unlike the most common local families, add a third. If the first spectrum lacks the usual gas features even as sunlight rises, we pencil a fourth. No single clue crowns the verdict, but together they lean the board toward visitor. Here is the what-if twist that makes this chapter feel like the future sliding into the present. Phone to telescope triage. Imagine a citizen network where your morning routine includes a simple app that pings when a new mover needs confirmation. You tap Available, and the app assigns you a task based on your gear. Have a small refractor on a balcony mount? You get a short sequence to check for a haze around the dot. Have a mid-sized backyard rig? You get a color pair to measure red versus blue brightness. Have access to a school telescope with a tiny prism? You get the 10-minute rainbow. The app handles pointing and timing, bundles your results with calibration stars, and uploads clean numbers to the central relay. In that breakfast window, dozens of volunteers can turn a rumor into a reliable profile. The system rewards good data with badges that actually matter, like priority assignments or access to live briefings. It is science as a shared habit, as ordinary as checking the weather. Not every ping will unveil a headline. Many will be honest locals going about their business. But now and then, the graph will tilt, the orbit will refuse to behave, and a sleepy city will wake to the news that a traveler from far away is cruising by. When that happens, those first 10 minutes will read like a heist montage. Quick cuts, crisp moves, and a satisfying click as the pieces fall into place. Next up, we move from triage to touch. How to design flybys, snatch samples, and pull off close looks without turning breakfast into lunch on cosmic timescales. Chapter 5, Chemistry in a Flash. Spectra as postcards from distant suns. Imagine you are handed a postcard with no words, only colors that shift when you tilt it under a lamp. That is what a spectrum feels like. It is light stretched into a barcode, and every little dip and bump is a letter in an alien alphabet. When a fresh traveler brushes sunlight our way, we can read those letters quickly to learn what sits on its skin and what hides just beneath. It is the scientific version of sniffing a stew and naming the spices. Earth is basically a rock that won the cosmic lottery. Spectra are how we read the ingredient list without opening the wrapper. Start with the simple truth that different materials are picky about light. Some grab certain shades and let others pass, the way a fussy eater pulls olives from a salad. If you shine broad daylight on a surface and then measure what bounces back, the missing colors tell you who did the grabbing. Ice-rich crusts like to nibble at very specific near-infrared shades. Water ice, for instance, leaves gentle notches at a few well-known wavelengths, while carbon dioxide ice prefers a slightly different set. Methane, ammonia, and methanol each carve their own signature dents. Minerals behave too, with iron-bearing rocks adding little sips of red, and silicate minerals shaping the mid-infrared like careful sculptors. The pattern of dents and curves becomes a fingerprint. We work fast because the visitor does not linger. A series of rapid reflectance spectra from the red edge of visible light into the near-infrared can outline the big families right away. A steep rise toward red often hints at complex organics crusted by long exposure to space weather, the kind of stuff that makes surfaces look like caramel-tinted frost. A flatter shape might mean fresher rock peeking out, or a veneer of clean ice. These are not final answers, but they are the first page of the postcard, the view from the balcony. Then we tilt the card. As the object rotates, fresh patches come under the lamp. A subtle dip that fades and returns tells us the surface is not uniform. Maybe there is a frostier cap on one side and a darker, older patch on the other. If the dips grow deeper as the sun angle changes, that can mean fragile ices close to the surface are waking up, whispering that a thin exhale of gas may be starting. We are not waiting to see a dramatic tale. We are watching the seasoning shift as the pan warms. Now the game turns to layering. Quick thermal spectra at longer wavelengths add a second dimension. Warmth from the sun radiates away, and the way it does reveals grain size and porosity. Think of it as a texture test. Fine powder cools and heats differently than compact crust. A surface that behaves like fluffy snow tells one story. A crust more like kiln-baked clay tells another. This thermally flavored spectrum pairs with the earlier reflected light to tighten guesses. The two together act like stereo hearing for chemistry. Next come the delicate hints of organics, not the dramatic chains found in living cells, but simpler rings and fragments that space cooks up in the quiet cold. Certain wavelengths betray the presence of aromatic structures, while others hint at aliphatic chains. If those notes appear alongside water or methanol signatures, you start to picture a freezer where chemistry has been marinating for a very long time. Short one-liner: photosynthesis is plants' way of saying they invented solar panels first. Meanwhile, interstellar chemistry is the way cold kitchens invent slow cookers. Every so often, spectra throw a party for the unexpected. Here is the what-if twist. Suppose our visitor shows a ratio of light grabbing that simply does not match any familiar recipe from our backyard. Imagine a combination where water ice lines look muted, while methanol sings loudly, or where the iron whisper in the rocks is stronger than it should be, compared with silicate cues. It would be like finding seawater pooled on a mountaintop with no nearby ocean. You would not jump to wild conclusions. You would first check your shoes and your map. Then, if the weirdness holds across several rotations and instruments, you start asking the fun questions. Did this object form closer to a faint red sun, where chemistry skews in a particular direction? Was it baked by a burst from a young star, and then deep frozen, locking in an odd mix? Did it pass through a rich cloud of molecules that painted the surface long after it left home? A deeper layer of clues lies in isotopes, the subtle mix of heavy and light versions of the same element. Even a rough measure, like the balance of heavy hydrogen in water, can point a finger toward a birthplace that had a different temperature history. We cannot tattoo those numbers on the object in 10 minutes, but we can catch a hint if outgassing reveals narrow features from certain molecules. A whisper of ammonia or carbon monoxide can tilt the story, especially when measured again a few nights later to see if the voice strengthens with warmth. Spectra also give away mechanical quirks. The way bands deepen and shallow as the object spins can reveal how rough the surface is at small scales. A glassy crust scatters light differently than a crumbly rind. If the surface is peppered with pits where ices once escaped, the light will tell on those pits. This matters because texture protects or exposes fragile compounds. A dusty blanket can hide fresh ice from harsh radiation, preserving chemistry that would otherwise burn off. Reading texture is like reading the house rules of the material. You can stay, you have to leave, you get a hat. The beauty of this approach is speed without panic. A well-rehearsed team can gather the core rainbow set within a single short window, spread across filters and thermal channels, and return a first sketch that is surprisingly rich. The sketch is not a final portrait. It is a postcard with a little scribble on the back. Wish you were here. The cliffs are redder than expected. The air smells faintly of alcohols. The pebbles crunch like glass. Black holes are the universe's way of saying delete browsing history permanently. Spectra are the universe's way of leaving tasting notes. If a visitor's fingerprint truly refuses to match any local catalogue, that oddness becomes a compass for everything we do next. The follow-up campaign targets the suspect bands with finer resolution, tracks how they evolve with warmth, and cross-checks with thermal behavior to see if buried layers are waking up. Each pass turns the postcard into a short chapter, and when the object finally slips away, we are left with a small library, colors, curves, and ratios that point back toward a different sun, a different winter, a different childhood than anything in our yard. Next time, we will trade light for approach, designing fast flybys and careful snatch and grab moves that let us taste the dust directly without wobbling the guest or our ambitions. Chapter 6: Touch and Go, Flybys, Rendezvous, and Sample Snatch Tactics. If discovery is the doorbell, engineering is the moment you decide whether to wave from the window or step outside with a handshake. Interstellar visitors do not loiter. They streak through like runners who forgot their headphones. That means our playbook favors fast, precise, and sometimes audacious moves. High-speed flybys that drink in detail in a heartbeat, dust skimmers that graze the wake, and clever nets that steal a few souvenirs without starting a tug-of-war. Think of it as polite piracy, with clipboards. Begin with the sprint event, the high-speed flyby. These missions accept that matching speed with the visitor is impractical for most cases, so they turn the relative velocity into a feature. Instruments are built like photographers at a finish line. You pack framing cameras with rapid shutters, a laser altimeter for instant shape and distance, a thermal imager to map warm and cool patches, and a dust detector that tastes particles as they ping past. Timing is everything. The spacecraft rehearses a camera choreography long before launch, acquire the target while it is still a glint, lock the tracking, and then ride a pre-planned scan pattern during the closest approach. Guidance relies on optical navigation. which is a fancy way of saying the probe watches the target against the background stars and adjusts its aim in real time. The risk is that small errors become big misses at very high speed, so redundancy matters. 2 independent trackers, overlapping fields of view, and a backup sequence that trades perfect framing for guaranteed coverage. If you only get one blink, you make that blink count. Now for dust skimmers, the daredevils of the fleet. A dust skimmer never tries to land. It swoops through the thin cloud that many small bodies shed when warmed. On board is a collector made from ultralight gel that catches grains gently, like snowflakes in a spider web. Because the encounter is violent at the particle level, the gel is layered. The first layer stops the speed, deeper layers preserve structure. Ahead of the collector sits a sacrificial bumper to soak up micro shrapnel, and the whole assembly is tucked behind a shield during the long cruise. At the moment of truth, a hatch opens, the skimmer angles its belly into the stream for a few precious seconds, and then the door swings shut. No touchdown, no anchor, no drama. Just a swift taste of the visitor's breath. Later, a small oven can heat a corner of gel, letting a sniffing instrument analyze released gases right there in flight, which is the space equivalent of sampling the soup before you bring the pot home. The net capture idea sounds wild, until you remember fishing is older than writing. Picture a small chaser that approaches on a crossing path and throws a fabric that blossoms into a cone. The goal is not to bag the whole object, which would be like lassoing a truck on a highway. The goal is to sweep through the halo of pebbles and dust that orbit or trail some bodies, especially those that are shedding. The net fibers are treated to trap grainy bits, electrostatically or magnetically, if the grains contain metallic flecks. Tethers keep the cone steady, and a quick spin winds the catch into a cartridge. Immediately after, the cone folds into a heat-safe pod in case the skirmish got spicy. It is quick, it is respectful, and it keeps the souvenir size to something customs would not frown at. Rendezvous is the dream move, the long conversation instead of the shouted hello. To do it, you need enough propulsion and patience to gently cancel most of the relative speed. That takes serious energy for a fast interstellar target, which is why Rendezvous will be selective. You might reserve it for the rare visitor that is big, bright, and announced early. The spacecraft would approach on a lazy arc, matching motion until the object becomes a slow companion. Then you can map the surface in detail, release tiny scouts to inspect craters, and even attempt a touch and go, a brief kiss with a sampling head that puffs gas to stir grains into a chamber and springs away in a heartbeat. The hardware borrows from recent asteroid missions, but adds armor and smarter autonomy. The surface may be unconsolidated, the spin may be odd, and the gravity is almost a rumor. Your landing foot should be more like a cat's paw than a boot. Shielding is the unglamorous hero across all these profiles. High-speed dust is sandblasting with a bad attitude. Whipple-style shields, thin plates separated by a small gap, turn incoming grains into sprays that dissipate before they hit the main hull. Sensitive instruments hide behind doors until the moment they are needed. The spacecraft's orientation during the pass uses its sturdiest face as a battering ram. After the encounter, the probe rotates to present solar panels or antennas only when the risk of debris is falling. Space may be quiet, but safety still sounds like a series of clicks and latches, working exactly as planned. Navigation deserves its own quiet applause. The target's path and spin are refined right up to the day of encounter, and the probe keeps learning. Star trackers feed attitude control with steady updates. A neural net trained on thousands of synthetic views compares real images to a library to find the limb of the object even in glare. Small thrusters make constant whisper-sized corrections. A companion CubeSat, if included, can fly slightly ahead as a scout, sending back a last-second map of hazards or unexpected jets. Redundancy, again, is the adult in the room. Here comes the what-if twist that makes all of this feel less like wishful thinking and more like a lifestyle. Modular probe kits on standby. Imagine hangars with ready-to-go spacecraft cores, fueled and stored like emergency vehicles. Each kit is a backbone with slots. Slot number 1, choose your camera suite based on brightness. Slot number 2, pick dust collector type, gel or net. Slot number 3, add a microspectrometer or a tiny thermal imager. The ground team assembles the loadout like a doctor, packing a specific first aid kit. A responsive launch rides whatever rocket is on deck that week, or even a high-altitude air launch plane that can sprint to the right latitude. From alert to ascent in days, not months. During ascent, the spacecraft uploads the freshest trajectory solution and plots a course that threads the needle between do not be late and do not be sandblasted. Because these kits exist in multiples, you can send a small swarm. One does the glamour flyby, another skims dust. A third lingers for a slower, wider pass that watches the visitor's behavior for hours. Data trickles back through relay craft or straight to big dishes on the ground. Each probe knows how to operate without a constant hug from home. Delays in communication mean autonomy is not a luxury. It is the whole personality. The joke writes itself. Space probes are that friend who can cook dinner, fix the sink, and host the party while you are still texting. On my way. When it works, the payoff is a time capsule cracked open while the clock is still ticking. We turn a nameless blur into a textured story. Surface rough as pumice here, glazed like toffee there, grains that carry the cold scent of long winters, tiny fragments that hum with minerals we rarely see together. We do not conquer anything. We borrow a teaspoon of history and give it a ride. In the next chapter, we will step back from the hardware and talk about traffic etiquette for a busier sky. Because a good neighbor policy is the quiet technology that keeps all these daring handshakes from turning into close calls. Chapter 7, Traffic Control. Space is a highway, not a parking lot. Picture orbit not as a quiet shelf, but as a multi-lane ring road wrapping the planet, full of delivery vans, research buses, weather scooters, and the occasional interstellar tour bus that forgot to signal. If the sky is getting busier, then etiquette becomes engineering. Traffic control in space is the invisible choreography that keeps everything moving without bumping elbows. It is not about telling the cosmos to behave. It is about teaching our machines to act like good drivers on a road that has no painted lines and no police stoplights, only physics and polite coordination. Start with the bulletin, the staple of any highway patrol. When a new object is spotted and its path is measured, a trajectory bulletin goes out. Think of it as a cosmic traffic report. Here is where the mover is. Here is where it is going. Here is how confident we are. The bulletin is time-stamped, signed so that no prank slips through, and pushed to anyone who might care. Satellite operators, space agencies, university labs, even serious backyard trackers who feed confirmatory data. This is not a dramatic siren. It is a calm voice saying there will be a fast guest near the outer lane at dawn. Please check your mirrors. Then comes conjunction screening, which is the space version of checking blind spots. Every satellite keeps a running calendar of predicted close approaches. When the new traveler is added to the map, software compares paths and flags any encounter that looks too cozy. The threshold is not a single magic number. It is a sliding rule that depends on size, maneuverability, and the fuzziness of the pass. If two objects might cross within a risky bubble, a yellow flag pops up. Operators watch that flag grow or shrink as better measurements roll in. Most flags fade with improved math. The rare ones turn orange, then red, and those trigger a plan. Avoidance maneuvers are elegant precisely because they are small. You do not yank a satellite into a new lane unless you have to. A short, well-timed push can change a meeting from uncomfortable to unremarkable, the way leaving 5 minutes earlier avoids rush hour. The trick is coordination. If two operators both dodge in the same way at the same time, you have invented a new problem. So, there is a courtesy channel. The first mover declares intent. The second acknowledges, and a common playbook decides who yields based on fuel reserves, mission priority, and whether one of the spacecraft is an unresponsive relic. It is orbital right-of-way turned into polite emails and crisp thruster bursts. Debris etiquette is the quiet backbone of this entire enterprise. When a rocket stage finishes its job, it should not linger like an empty shopping cart in the middle of the aisle. Passivation, safely venting leftover propellant and power, keeps dead hardware from popping like unplanned fireworks years later. When a satellite reaches retirement, it climbs into a graveyard orbit or aims for a controlled re-entry over empty ocean. Meanwhile, ground and space-based radars, optical telescopes, and laser ranging stations keep tabs on the small stuff. Even a paint chip can scuff a mirror at highway speed. Tracking those specs is like counting raindrops with a stopwatch, but every bit helps. The unglamorous rule holds: leave the orbit cleaner than you found it, or at least not messier. Now layer in the incoming visitors. Most will never get close enough to pose a threat to anything in low Earth orbit, but a few pass through the broader neighborhoods where navigation satellites and weather sentinels live. Trajectory bulletins for interstellar guests include a courtesy corridor, a safe distance band that says, steer clear during these hours just in case. Operators can rotate sensitive instruments away from the oncoming flow, power down vulnerable sensors for a few minutes, or simply switch to a mode that shrugs off stray dust. No panic, just umbrellas up until the cloud passes. Here is where the imagined future becomes refreshingly practical: a shared space lanes map that updates live. Picture a public, neutral dashboard, run like air traffic control, but open and machine-readable. Every active spacecraft publishes a basic state vector, a formal way of saying here is where I am and how I am moving, along with a plan for the next few hours. The map fuses this with tracking data for uncooperative debris and with the freshest path predictions for natural objects. It does not show sensitive details, but it shows enough to prevent awkward surprises. A satellite operator can subscribe to a region of sky and receive clear, simple prompts. Hold attitude for 2 minutes at this time. Nudge along this direction after sunset. Avoid high-gain pointing when the visitor's dust cone peaks. The interface behaves like a navigation app that respects fuel budgets and mission goals. To make that map work, standards have to be friendly. Time must be stated the same way by everyone. Positions must use the same reference frames. Uncertainties must be honest, and updates must be frequent enough to matter, but not so frantic they drown operators in noise. Automation can help here too. Smart filters highlight only the items relevant to each vehicle's lane and purpose. A weather satellite does not need warnings meant for a deep space probe, and a small cube on a tight budget should never be told to spend fuel it does not have. Civility extends to launches. Rockets depart through corridors that avoid crowded slices of sky, the way planes observe quiet zones over cities at night. A launch window is not only about weather and trajectory, it is also a courtesy to satellites already in place. The shared map can temporarily paint dynamic keep-out zones around ascents and re-entries. Everyone sees the arcs. Everyone plans around them. No guesswork, no surprise cameos in someone else's camera frames. The payoff is peace of mind without complacency. Instead of hoping the sky takes care of itself, we act like neighbors who put the bins out on the right day and keep the sidewalk clear. The difference is that our sidewalk moves very fast and wraps the whole world. When a traveler from far away cuts across the outer lanes, the map glows softly, satellites take small breaths at the right moments, and the guest sails through without a single cosmic fender bender. And that sets us up for the next move. Once we know how to share the road gracefully, we can practice gentle pushes and careful rehearsals on harmless passers-by. Planetary defense, not as a panic scramble, but as well-rehearsed muscle memory. Tomorrow, we will train on friendly targets and learn how a slight nudge today can save a headache years down the lane. Chapter 8, Planetary Defense. Practiced on friendly targets. Imagine signing up for a fire drill where the building is not on fire, the exits are clearly marked, and there is free lemonade afterward. That is the spirit of practicing planetary defense on harmless visitors. We are not waiting for a last-second sky problem. We are building calm routines on safe, non-threatening objects that happen to wander close enough for a test. It is the difference between learning to parallel park on an empty Sunday street and trying it for the first time during rush hour with a marching band crossing. First, the gentle nudge. Think of a small spacecraft as a polite shoulder tap. It approaches a target that is comfortably far from anything important and gives the tiniest push by bumping at a carefully chosen spot and speed. No explosions, no movie soundtrack, just a momentary kiss that changes the object's path by a hair's width. Sensors watch before, during, and after, measuring how that whisper of momentum turns into a long-term drift. The value is not the drama, it is the calibration. We learn how real rocks respond, how surface fluff absorbs energy, and how a small push translates into a safer orbit down the calendar. Space objects can be like stubborn grocery carts. If you nudge the wrong corner, they wiggle instead of moving. Training turns guesswork into a playbook. Next, the gravity tractor, which is less tractor and more patient tow truck that never hooks up. Park a spacecraft near the visitor and let mutual gravity do the work. The craft holds position with thrusters, ever so slightly tugging the object over weeks or months. It is the cosmic version of standing on a rug and slowly dragging it with your toes. Practicing this technique on friendly passers-by teaches us the art of hovering in weird, lumpy gravity fields without wobbling or wasting fuel. It also teaches restraint. If you get too close, you risk stirring dust or bouncing off a boulder too far, and you are a polite observer rather than a mover. The sweet spot is a dance floor, not a bullseye, and practice finds the tempo. Now unleash the swarm scouts, a flock of tiny, cheap satellites that can spread out like curious pigeons around a statue. Each scout carries a simple camera, a radio, and one job: map, measure, or ping. One might study spin by timing sun flashes. Another might bounce a faint signal to probe inside structure. A third might drift through the faint dust that clings to the object's wake. Swarms are not just backup cameras. They are how we see the unexpected. A hidden moonlet, a soft patch that crumbles under light pressure, or a jet that sneezes when warmed. Practicing with swarms on calm targets teaches the craft to wrangle their own choreography, pass data efficiently, and avoid playing space bumper cars with one another. All of this is framed by ethics and etiquette. A friendly target is chosen because any change will remain safely distant from Earth and from other assets for many decades. We post the plan in public: how much push, how long the hover, where the scouts will roam, how we will measure results. Transparency prevents misunderstandings and invites clever minds to double-check our math. The point is not to flex muscles, it is to build trust in techniques that might one day be needed when time is tight and stakes are high. The payoff from rehearsal is a library of response curves. Real rocks are mischievous. Surfaces can be powder soft in one region and crusty in another. Spin can wobble like an unbalanced top. A nudge on the equator differs from a nudge near a pole, and a push that is perfect at dawn may behave differently at dusk as the surface warms and cools. By running multiple trials on multiple harmless visitors, we learn which combinations give clean, predictable results and which give noisy surprises. The result is not a single magic maneuver. It is a menu with clear labels. Use this for slow tumblers. Avoid that for gravel piles. Choose this when the object has a companion. Here comes the delicious what if. Suppose repeated drills reveal a timing window that is almost too good. A tiny push applied when the target is at a very specific point in its path multiplies over decades into a graceful sidestep. Miss that window by a year, and you need 10 times the effort later. Miss it by a decade, and you might need heroic measures no one wants. Finding this sweet spot is like discovering that turning your steering wheel a finger's width at the right intersection saves you from a roadwork snarl many neighborhoods away. In practice, that means we would not wait for late warnings. We would keep a running list of non-urgent objects and schedule miniature corrections during the golden moments when effort buys maximum safety. Critically, practice sharpens our ability to predict side effects. A nudge changes spin as well as path. A gravity tractor can coax tiny grains into motion. A swarm can shade a patch of surface long enough to ice it slightly. These are not disasters, but they are real. Drills teach us how to avoid domino chains, how to back out gracefully if a measurement goes sideways, and how to leave the target in a state that still makes sense to future observers. Space is not a place to leave puzzles wrapped in red tape. Communication is part of the craft. Each rehearsal is narrated in plain speech so that people outside the engineering tent can follow along. What we are doing, why this object was chosen, how small the change will be, and how we will verify the outcome. The day we truly need these moves, confidence will rest on more than clever diagrams. It will rest on memories. We have done this, we saw the data, we learned the quirks, we know the knobs to turn. There is a quiet dignity to training for a crisis that may never come. It is the opposite of panic. It is practice with a smile. Think of harmless visitors as volunteer coaches. They fly by, we learn a little patience and finesse, and everyone leaves a bit wiser. Somewhere in those drills, we will map the generous window where a feather touch today prevents a heavy lift a century from now. And that brings us to our next task, keeping the science clean as the stakes rise, with sterilized tools, pristine chambers, and protocols that treat alien dust like both treasure and responsibility. Chapter 9. Clean Rooms and Clean Conscience. Biosecurity for Alien Dust. Imagine the moment a capsule returns with a thimble of dust that took the long way home through interstellar winter. Everyone wants a peek. No one gets to breathe on it. This is where curiosity wears a lab coat and a seatbelt. Clean rooms and careful rules are not the villains that slow down discovery. They are the quiet heroes that make sure the story in that dust is the dust story, not a remix with fingerprints from half the planet. Earth is basically a rock that won the cosmic lottery. Now we prove we can handle the winnings without smudging the ticket. Contamination control starts long before a sample is anywhere near Earth. Every tool that will touch the material is manufactured, baked, and packaged under air that has been scrubbed by high-efficiency particle filters. Surfaces are rinsed with ultra-clean water and solvents that are tested for background molecules. Metal parts go through dry heat sterilization. Delicate pieces meet gentle plasma or ultraviolet light to shake off stubborn hitchhikers. The target cleanliness is not a vibe. It is a measurable absence of particles, oils, spores, and stray molecules that could masquerade as interesting chemistry later. We add witness plates to the flight hardware, tiny clean coupons that ride along and collect the same environmental crud the sample might see. Later, those plates tell us what contamination we brought to the party, so we can subtract it with confidence. Next comes the theater of arrival, and it plays like a heist, where the prize is integrity. The sample capsule lands at a remote site, and the first hands it meets are gloved inside a portable tent that keeps out dust and breath. The tent is a mini clean space with its own filtered air, anti-static floors, and a log that records every sneeze the tent ever had. The capsule is bagged, crated, and flown directly to a curation facility designed like a Russian doll. Rooms within rooms, pressures stepping inward from higher to lower, so that air always flows into the most protected chambers, never out of them. Doors interlock, so only one opens at a time. The whole place hums quietly like a library with a very serious HVAC degree. Quarantine is not punishment. It is wisdom with a calendar. We do not know the biological status of interstellar dust, and we do not pretend we do. So the sample enters containment that treats it as if it could carry unknown chemistry or biology, even if the odds are small. The first chamber is for non-destructive exam only. Weigh, image, sniff. Instruments measure tiny outgassed molecules with care. while air from the chamber is scrubbed and monitored before it leaves the building. Waste is not thrown away. It is catalogued, sterilized, and archived as carefully as the sample itself. If life taught us anything, it is that leftovers can be loud. Chain of custody is where clean conscience meets clean room. From the instant the capsule door opens, every movement of the sample is recorded in a signed, time-stamped digital ledger, mirrored in multiple places. Labels with unique identifiers follow each fragment and each aliquot. 2 people, not one, witness every transfer, seals that show tampering guard every container. Think courtroom meets lab bench. The goal is simple. Decades from now, another scientist must be able to reconstruct the full journey of a grain and know exactly who touched it, when, and under what air. Now the fun twist, customs at the edge of the atmosphere. What if we build a portable clean lab that rides to low Earth orbit and meets the sample before it dives through our weather? Picture a small, free flying module that docks with a returning capsule, or a courier craft. Inside is a glove box with space-rated seals, microscopes, a gentle saw for subdivision, and miniaturized analyzers that can read gases, scan surfaces, and even do first-pass isotopic checks. The module's air is recirculated through brutal filters and then gently exhausted into space, not into us. If the analysis says this is stable and safe to bring down, small parcels are sealed in multi-layer containers and sent to the ground curation center. If anything raises a question, unusual volatiles, reactive grains, or just a surprise, data goes to mission control and protocols shift. The rest can wait in orbit, where vacuum is free and containment is easier. It is border control with a view. Inside the ground facility, separation is sacred. There are dedicated lines for organic studies, mineral studies, and volatile studies, each with their own tools and their own air, so a sniff of alcohols does not wander into a mineral microscope room. Tools never hop aisles. If you need a saw in another line, you have a second saw that has never met the first. Every action is matched with blanks and standards. Handle a piece of sample, handle an empty tray in exactly the same way. Analyze both and keep the difference. That difference is the truth. People are part of the system, and people are messy, so they are wrapped in layers of discipline, gowns, double gloves, hair covers, and training that drills muscle memory until no one casually reaches across a clean surface. Entry rituals slow you down on purpose. Wash, suit, lint roll, air shower, step mats. Jokes are allowed, shortcuts are not. Photosynthesis is plants' way of saying they invented solar panels first. Clean room etiquette is humanity's way of saying we invented patience for a reason. Communication matters almost as much as filtration. The world will want updates. The answer cannot be, trust us. So the lab publishes live dashboards of environmental readings, particle counts, microbial assays of air filters, chemical fingerprints of cleaning solutions, and the running chain of custody for public audit. Data that cannot reveal the sample's secrets still reveals the lab's honesty. When results do come, they arrive with the context to believe them. If a trace of methanol appears, we show the blank that did not. If a rare mineral pops, we show the witness plate that proves it was not lurking on the tool. What about the humans who handle this precious dust? They are monitored too, out of respect for both directions. Backward contamination, anything that might affect Earth, is guarded by medical checks and by personal quarantines if a protocol is breached. Forward contamination, us leaving our life crumbs on the sample, is guarded by training, by redundancy, and frankly, by pride. The culture inside a curation facility is 1 part craft guild, 1 part orchestra. Everyone knows their part, and the symphony is purity. Handled this way, a teaspoon of alien dust becomes a time capsule we can open without losing the message. We do not promise drama, we promise clarity. And clarity is the currency that lets science move fast without tripping. Next, we will change gears from conscience to commerce and explore how a steady trickle of visitors could spark practical markets in orbit, water wells, way stations, and startups that think space logistics are just camping with better spreadsheets. Chapter 10: Economics in Orbit, Mining, Markets, and Moonshot Startups. Imagine a frontier town that never sleeps, except the saloon is a refueling depot, and the general store sells sunlight, tanked water, and spare reaction wheels. That is the vibe when interstellar visitors and near-Earth wanderers turn from curiosities into resources. The story is not gold rush chaos, it is careful logistics. Space mining is basically camping with better logistics. Start with the most boring treasure that turns out to be thrilling: water. A rock with frozen water is a mobile reservoir. Melt it, filter the grit, and you have 3 valuable products. First, drinking water for crews. Second, radiation shielding when packed as liquid around habitats. Third, propellant by splitting water into hydrogen and oxygen, then chilling it into dense liquids. A depot stocked with those liquids turns hard missions into easier ones. Instead of launching every drop from the ground, vehicles sip along the way. That single shift rewires mission math without writing an equation on a chalkboard. Metals are the second pillar. Many small bodies carry nickel-iron cores, peppered with cobalt and precious elements. In orbit, you do not need to ship jewelry. You build structure. Melt nickel-iron in a sun-powered furnace, and you can cast beams, plates, and pressure vessels without fighting gravity. Additive manufacturing in microgravity makes trusses that would sag under their own weight on Earth. A future communications array might have a frame born from a boulder that once wandered between planets, its mirrors polished by robots who never complain about overtime. Volatiles beyond water add texture to the business plan. Ammonia becomes fertilizer for space-grown greens, methane becomes a fuel for certain engines, and carbon-rich compounds become feedstock for plastics and rubbery seals. A small chemical plant bolted to a miner can turn a bland rubble pile into a mixed palette of goods that other spacecraft actually need. The key shift is psychological. We stop viewing small bodies as dangerous pebbles to dodge and start viewing them as service stations laid out by physics. Who builds this? A ladder of startups that specialize, fail fast, and occasionally amaze. Prospectors map and sniff, selling data about which rocks are worth visiting. Excavators design gentle tools that lift grains without blasting shards into everybody's orbit. Processors handle heat and chemistry, tuned for vacuum and stingy on power. Haulers use efficient electric thrusters to ferry tanks and crates between depots and customers. Depot operators are the hoteliers of space, trading storage, thermal management, and quality control for a fee. Then there is a quiet hero class, insurers who price risk and auditors who verify that a drum labeled water is not a drum of hope. Refueling depots will start where they are easiest, in high Earth orbit and at the balance points between Earth and the Moon. Those are natural crossroads where many missions already pass. A depot there needs big tanks, careful thermal blankets, and the discipline of a submarine. Boil off is the enemy. You fight it with reflective skins, sunshades, and smart chillers that sip power only when needed. A steady schedule of arrivals and departures keeps inventory fresh and equipment honest. Every transfer is metered, sampled, and logged, because reputation is the oxygen of an orbital business. Now for the delicious what if. A captured water-rich boulder becomes the first true space well. Picture a modest rock shepherded into a safe, high orbit with a gentle, years-long tug by solar electric propulsion. Engineers wrap part of it in a tailorable blanket and embed coils that gently warm select pockets. Out seeps vapor. Condensers harvest it into clean tanks. No blasting, no fracturing, just a geothermal spa in microgravity. The well stays put for decades, visited by tankers that top up and glide on. A plaque could read, "This station once circled the sun alone, Now it keeps travelers moving. It is quaint and revolutionary at the same time. Stewardship is not an afterthought. It is the operating system. Before touching a target, crews run an environmental impact assessment, customized for vacuum life. Will excavating loosen debris that could threaten neighbors? Can we bag fines and vent dust only when we face empty space? Where do we park spent shells so they do not drift into busy lanes? Every miner carries a cleanup kit, nets for strays, adhesive pads for fines, and a final pass routine that leaves the scene quieter than they found it. Telemetry is transparent by default. Fuel burns, venting events, and transfer logs are broadcast to a shared ledger that other operators can audit. Trust is not a handshake, it is a trail of receipts. There is also the human side. Workers in orbit will not be pickaxes on cliffs. They will be pilots of telerobotic crews, layered with autonomy. Shift changes follow sun cycles. Break rooms are camera windows with views that make coffee taste like a celebration. Training programs blend spaceflight safety with industrial hygiene and the patience of a jeweler. A good operator knows when to pause because a shadow changed and the surface might be telling a new story. Markets will grow in funny directions. A science mission buys a tiny vial of hyper-pure grains for a lab study. A tourism craft pays a premium for safe, certified water to fill a zero-gravity tea ceremony. A construction group leases a beam printer and buys spools of orbit-forged alloy. A weather satellite consortium buys propellant credits 5 years in advance to guarantee station keeping through a rough solar cycle. Each sale is small at first, but habits become infrastructure, and infrastructure is destiny with a timesheet. Of course, not every rock becomes a storefront. Many will remain scenery, and that is fine. Selectivity avoids waste and preserves the wonder that draws us up there in the first place. The real victory is not conquering material, it is learning to live well with it. When a depot manager can say, "We met our safety goals, our emissions were near zero, and our ledger balanced without cutting corners," you will know the frontier has grown up. Economics in orbit is not a fever dream. It is a series of careful Tuesdays where tanks fill, invoices clear, and robots do chores while no one watches. Somewhere between those Tuesdays, someone will hang a small sign on a calm, captured boulder that simply says, "Well, number one." When that happens, artists and storytellers will not be far behind, ready to rename constellations and set their lyrics to the soft hum of depot pumps. And that is our next stop, the culture that blooms when the sky keeps sending guests and we keep answering with music, stories, and a little sparkle. Chapter 11, Culture Shift. From poetry to pop songs to public art, the first time a stranger from deep space glides through our neighborhood. Scientists cheer and anchors practice saying the name without tripping. The second time, something different happens. The city listens. Genres bend. A designer swaps her color palette to match a spectrum chart. A poet writes in stanzas the length of a light curve. A kid hums a melody that rises and falls like a brightness plot because it just feels right. Culture has a way of pirouetting toward whatever keeps returning. If visitors keep arriving, art will meet them at the curb with a sketchbook and a drum. Names change first, because names are how we invite things into the family. Instead of a handful of star heroes and mythic beasts, we start naming after moods, places, and communities that helped find them. A visitor discovered by a high school team during a pre-dawn session might carry the school's mural theme into the catalogue. Another could be named for a river that once carved the town where the small observatory sits. There will be public ballots that feel less like popularity contests and more like neighborhood potlucks, with a rule set that guards against the old habit of stamping faraway things with the same few stories. Curators will nudge the tradition toward equity, a chorus of languages, a balance of histories, respect for the sky as a commons. Then come the narratives. Filmmakers learn to frame tension around a passing object that will be gone by next week. You do not need explosions when your antagonist is time itself. Short films follow volunteers who set alarms for 3 in the morning and stumble to rooftops with thermoses, catching a ghost on the move. Graphic novels give each visitor a voiceover, not as a person, but as a diary of the materials it carries. I remember a winter around a dim red sun. I remember a near miss with a giant planet that tossed me like a pebble in a sling. Children's picture books will trade rockets for welcome mats, drawing the solar system as a house with a front porch light left on. Music folds the sky into its bones. Producers turn spectra into chord progressions, mapping deep dips to bass lines and bright peaks to high strings. Live shows project real-time trajectories across the stage, and dancers move along arcs that mirror predicted paths. A summer playlist might open with an interlude called Incoming, a 2-minute instrumental built from sonified telemetry. Street musicians sample antenna hiss during a meteor shower and turn it into percussion. Photosynthesis is plants' way of saying they invented solar panels first. Artists will say they invented cosmic mood boards. Public art does what it always does. It makes the invisible sit still long enough for us to breathe. On the side of a library, a mural shows a map of the sky, with the faint dotted lines of visitors from the last decade, each line in a different hue. At night, projection mapping animates those dots into tiny comets that drift across the brick, while a caption at street level explains the colors in words a child can hold. Parks install kinetic sculptures that slowly rotate to match the changing position of a known traveler as it returns to the deep. In train stations, small light displays blink when a new object is confirmed, and for a few seconds, the crowd lifts its eyes for reasons that are not about arrivals and departures on the ground. City rhythms shift to make room for the sky. Light pollution is no longer a dry policy issue. It is a civic pride project with stickers in cafe windows that say, "This block dims for the sky." Neighborhoods coordinate gentle dark hours during predicted peaks, the way seaside towns schedule tide festivals. Rooftop lounges become microplanetariums with blankets, warm drinks, and quiet rules. Schools host sleepovers under gym roofs that retract for a shared look at a fast traveler before homeroom, and the hallways ring the next morning with stories that start with "you had to be there." Merchants and makers find tasteful niches that celebrate without cheapening. A ceramicist glazes bowls in the hues of a particularly famous spectrum, labeling them with the story of the night it was taken. A tailor stitches subtle arcs into a jacket lining to echo a favorite trajectory. Cafes offer a once-a-month visitor night menu, with dishes named for the mood of the sky. No gimmicks, just a reason to gather. Meanwhile, museums reimagine what a permanent exhibit means when the content is always moving. Rotating galleries curate a decade of arrivals, as if they were seasons in a long show, with listening booths where you can hear the audio version of a light curve, and talkback stations where visitors leave haiku inspired by last night's image. Language picks up souvenirs. New idioms sneak into everyday chatter. A person who breezes through town becomes a passerby with a good spectrum. A sudden idea is an incoming object with a bright core. A beloved elder is a long-period friend who keeps returning when the calendar needs them. Emoji packs add tiny arcs and dots so texts can say "meet you under the visitor" without spelling it out. Education stops pretending that science and art live in separate apartments. Literature classes assign poems that riff on orbital predictions. Art classes paint with palettes extracted from actual measurements. Music students collaborate with physics clubs to score a morning flyby and perform it at assembly. The message is gentle and obvious. The sky is not homework. It is culture. Here is the what if that feels inevitable once the habit sets in. Meteor showers, seeded by interstellar fragments, become annual city festivals. The schedule is penciled into the civic calendar like harvest parades. On the big night, the city dims non-essential lights, and the main boulevard hosts silent concerts where the music listens for the soft radio crackle of meteors, ionizing air, Food carts serve warm bowls and patient drinks, and a children's procession carries handmade paper comets with tails of shimmering ribbon. There is no countdown because the sky does not take requests. Instead, the crowd settles into the oldest human posture, heads tilted back, mouths open, stories rising and falling with each brief streak. The morning after, the street crews leave the pavement cleaner than they found it, and the only trace is a chalkboard at the museum tallying last night's count in careful words. Culture will not orbit science like a satellite. It will braid with it. Visitors from far away will teach us to treat wonder as a civic habit, as ordinary and vital as good sidewalks and open libraries. Next, we turn the lens from our stories to their stories, asking how the tiniest shavings from a traveler can let us reconstruct the weather and history of a sun we have never seen up close. Chapter 12, Clues to Other Suns. Forensic Exoplanetology. From Pebbles, picture a crime lab where the suspect is a grain of dust, and the motive is the story of a faraway sun. Forensic exoplanetology sounds grand, but the craft is disarmingly humble. Take a shard that crossed the dark for ages and read the tiny clues frozen inside it. No equations on chalkboards, no dramatic courtroom speeches, just quiet instruments, steady hands, and the realization that every speck is a travel diary written in the alphabet of atoms. Start with isotopes, which are like regional accents for elements. Hydrogen can be light or heavy. Oxygen can be common or slightly heavier. Carbon can speak in different weights. The mix of these versions is not random. It carries the weather report and family history of the place where the material formed. Heavy hydrogen tends to gather where temperatures were low for a very long time. Heavier oxygen versions can whisper how water cycled between ice and vapor. Carbon's balance can hint at whether the material grew up near a bright young star that shouted with fierce light, or in a calmer suburb of the galaxy. Why do these accents point to star types? Because different stars shaped their neighborhoods in different ways. A red dwarf, small and thrifty with light, gives its worlds long winters and slow chemistry. A hot blue star floods everything nearby with harsh light that scrubs fragile molecules and rearranges isotope balances like an overzealous editor. Even two sun-like stars can diverge if one was born in a metal-rich nursery and the other in a leaner cloud. Element richness sets the pantry for planet-making, and the pantry leaves fingerprints on every cookie that ever crumbled off a world. Trace gases trapped in tiny glassy pockets are the headliners here. Noble gases, those famously aloof elements that prefer to mind their own business, are perfect witnesses because they do not react much. Neon, argon, and xenon, boxed into microscopic bubbles, carry a time capsule of the pressure and radiation environment where the pocket formed. Their ratios compare like swatches of color on a designer's board. This shade matches systems with flaring young suns. That shade matches older, quieter neighborhoods. Add a hint of nitrogen or sulfur-bearing gases, and you begin to sketch the air that might have brushed the surface where this grain last rested. Minerals round out the picture with their own silent testimonies. Crystals, such as olivine and pyroxene, tell you the furnace temperature they survived, while sulfide grains betray the presence of a low oxygen environment during their birth. Some salts form only when liquid water lingers and then dries, leaving crusty signatures that are impossible to fake without a real wet past. A shard, carrying both high-temperature crystals and delicate salts, reads like a trip itinerary, born in heat, traveled through cold, paused where water once pooled, then ejected into the dark by some grand pinball event. The lab procedure is a careful dance. A tiny chip is shaved from the shard and warmed until imprisoned gases whisper out. Instruments listen, separating the whispers into voices and measuring how much of each voice is present. Another slice is gently ablated with a narrow beam until plumes of atoms drift into a detector that counts the heavy and light versions one by one. Each count adds a pixel to a picture that no camera can take. If this sounds fussy, It is, but fussiness is how you turn a postcard into a map. Now for the delicious what if. Suppose a shard carries salts that do not match any simple ocean recipe we know, not because the names are strange, but because the proportions sing a different tune. Imagine a mix richer in bitter salts than our seas, paired with trace boron and lithium in ratios that do not line up with any common Earth rock catalogue. You would not shout alien beach right away. You would test the tools twice and check the blanks for sneaky contamination. But if the signature holds, you would have a story. Somewhere out there, a world had long lived water-rich basins that evaporated in a way unlike our coasts, perhaps under a sun that rose weaker or over crust that fed the water through unusual rocks. The shard becomes a brochure for a shoreline you have never seen, complete with a taste of the spray. Isotopes deepen the travel guide. Heavy hydrogen, richer than typical, tells you the water lived in cold storage for long spells. Oxygen, with a skewed balance, hints at cycles of freezing and thawing under a thin atmosphere. Carbon that leans toward heavier voices suggests chemistry, nudged by light, that was strong in certain bands. The kind young red stars dish out when they tantrum. String those together, and a sketch emerges, a small world around a patient star, with seasons that last an age, an atmosphere that comes and goes, and lakes that concentrate salts into layered crusts before the climate slides again. Even the way grains are glued together tells tales. If the shard is a rubble of rounded pieces locked by fine dust, it formed in a gentle environment where collisions were slow enough for fragments to cuddle rather than shatter. If edges are sharp and bruised, the shard was born from a violent break. Microscopic craters on the surface record a lifetime of tiny impacts, their depths and densities acting like the rings of a tree, with spacing that speaks to how long the shard drifted in open space versus hiding inside a larger body. We can also triangulate formation zones without drawing a single orbit. Materials that condense at higher temperatures point to inner disk neighborhoods. Frosts that could only stabilize far from a star point to outer regions beyond the waterline, beyond the carbon monoxide line, and so on. When a single shard holds both types, it means migration. Grains wandered inward and outward before locking together, or a parent world mixed material across huge distances, perhaps stirred by a roaming giant planet. The galaxy, it seems, loves a road trip. One wry reminder keeps the whole enterprise honest. Nature enjoys reruns. Different systems can produce similar chemistries by different routes. That is why the lab keeps layering evidence, gases, minerals, isotopes, textures, until a pattern is overdetermined. Only then do we dare say, this pebble was probably raised under a red sun with an iron-rich pantry, or that fleck likely formed near a quiet star where cold ruled and water learned patience. In the end, the smallest bits become ambassadors. They cannot show us a horizon, but they can show us a menu. The air that might have been breathed by rocks, the water that might have licked shores, the heat that once wrapped newborn worlds. It turns out a dust mote is a telescope that looks inward instead of outward. Next, we turn from the poetry of what these shards reveal to the paperwork of how we share them, who gets a say, who holds the keys, and how to keep cosmic heritage from becoming a tug-of-war on a very big porch. Chapter 13, Law and Ethics. Who owns a visitor? Passing everyone's backyard. Picture a pebble from far away, drifting through the solar neighborhood like a stray letter with no return address. Telescopes spot it. Teams line up to study it. A startup wonders if it could harvest a little water. A museum dreams of a display case with stardust under soft lights. Then the question lands with more weight than the pebble itself. Who gets to decide anything about this traveler? The awkward answer is that space law is a patchwork quilt, warm in places and threadbare in others, stitched together by ideals written before passing visitors became a routine headline. The baseline is simple and noble. No nation may claim a celestial body as its property. Space is a commons for peaceful purposes. Actors must avoid harmful contamination and show due regard for one another. That spirit says no flags as deeds and no fences around the sky. But it says less about an object that is just visiting, has no caretaker, and might be reachable for a quick sample that could change textbooks. We have rules for planets and orbits, and a growing playbook for satellites and debris. Stray interstellar mail is a new corner case. And corner cases are where ethics prove their fitness. Ownership is the wrong first word. A better starting point is custodianship. Custodianship means you hold something for the benefit of many, protect it from harm, and document what you do so that others can trust the story. Think museum, not pawn shop. Applied to a visitor, custodianship would ask, what are the risks if we touch it? What are the gains if we learn from it? And how do we make sure the gains are shared rather than hoarded? A custodian keeps receipts and leaves the door open for peer review. Even stronger is guardianship, which leans toward protection before extraction. A guardian assumes this traveler is part of a wider natural heritage, like a rare manuscript that fell off a shelf in a public library. You may read it, you may copy a page under bright lights that will not fade the ink. You may not tear out chapters because you like the paper. Guardian first, researcher second. That stance is not anti-business, it is pro-future. It says the object's story should outlast any quarter's balance sheet. Treaties give shape, practice gives teeth. A sensible path begins with registration. The moment a visitor is confirmed, it goes into an open registry with a neutral host. Every planned activity around it must be logged. Observations, flybys, sampling attempts, even proposals to nudge it for safety drills. Each log comes with an environmental note that explains potential effects, mitigation steps, and a plan to monitor outcomes. Think public notice boards, but with better handwriting and fewer stapled flyers. Next comes consent, a tricky word when no one speaks for the rock. Here, consent means broad human agreement, a committee of stakeholders, a mix of scientists, engineers, ethicists, indigenous knowledge holders, legal scholars, and public voices, reviews plans against a clear checklist. Is the action reversible? Is the sample size minimal and justified? Are there safer alternatives? Will data be shared promptly? Is there a plan for cleanup and for reporting unintended side effects? This is not bureaucracy for its own sake. It is a speed bump that keeps rush and regret from becoming roommates. Commercial players are part of the picture, and they need clarity, not scolding. The rule set can invite them in through a benefit-sharing framework. If a company performs a capture or processing step that yields useful material, a portion of the value flows into a global trust that funds open science, public archives, and safety infrastructure. Transparent ledgers show who paid what, who received what, and how decisions were made. Call it a sky tithe, modest and meaningful. It turns private enterprise into a partner in maintaining the commons rather than a tenant trying to rewrite the lease. Data is where fairness becomes real. A visitor will not wait while a non-disclosure agreement is negotiated. So the default should be open by design. Post the orbit, the light curves, the spectra, the images, the sample metadata, and the processing steps in public repositories with timestamps that credit contributors. Proprietary periods can be short and clearly defined, like a brief head start for the team that caught the ball, not a wall around the field. Credit is a powerful currency. Share it widely, and you prevent a lot of ugliness. Disputes will happen. Build an arbitration lane before tempers flare. A standing panel can mediate conflicts about scheduling, sampling rights, or safety concerns. Its decisions should be published in plain language, so future teams learn the lessons without repeating the argument. Transparency is the adult in the room. Secrecy is what invites rumor to host the after-party. Here is the hopeful what if. A global trust model where humanity shares samples, data, and decisions. Imagine a charter that treats interstellar visitors as a special class of cosmic heritage. The trust owns nothing, It coordinates everything. Members include spacefaring nations, emerging programs, private firms, universities, museums, and citizen networks. The Trust issues temporary permits for actions large and small, holds a central registry, and maintains a public dash that shows plans and progress. Sample custody is documented from scoop to microscope. Digital twins, meticulous records of each fragment and each analysis, are preserved so that a student 10 years from now can reanalyze the same evidence with new tools. The Trust also sets gentle red lines. No deliberate fragmentation of intact travelers unless a safety case is overwhelming. No long-term privatization of unique samples. Aliquots may be loaned under strict conditions, but heritage pieces remain in public curation. No data dumps without context. Raw numbers must travel with methods and limits so they can be used honestly. And always, a bias toward minimal touch. When in doubt, take fewer grains, share them better, and tell the story in full. Ethics thrive on habit. Ritualize the good stuff. Before a mission approaches a visitor, host a public briefing with clear words and no sales pitch. Afterward, publish a plain summary alongside the technical paper, what we did, what changed, what surprised us, and what we chose not to do. A little humility travels far. So does humor. If Patience had a logo, it would be a gloved hand, giving a thumbs up next to a sealed file. In the end, the question, who owns this, becomes a gentler one. Who is responsible for this, for now, on behalf of everyone, later? Ownership is a lock. Guardianship is a promise. Visitors from far away are not trophies, they are teachers. If we build a system that honors that, we will look back at this era and feel something rare in law and policy, pride without footnotes. Next, we will step out of the council room and into the night again, to read the sky's quick handwriting, brief glows, and vapor trails that turn chemistry into fireworks, and give us weather reports from rocks that never learned to sit still. Chapter 14, Weather in Space, predicting showers, grazes, and glow trails. If the nightly news can tell you when umbrellas beat sunglasses, why not when to grab a blanket and watch the sky sprinkle? Space has weather, not with clouds and rain, but with tiny fragments that paint the upper air and whisper what they are made of as they burn. A grain smaller than a seed can throw a light show, and, for a heartbeat, turn chemistry into handwriting. Begin with the stage. Far above jet trails lies a cold, thin realm where air molecules are more rumor than crowd. When a fragment enters that realm at very high speed, friction is not quite the right word. Compression is. The air just ahead of the fragment squeezes and heats. The fragment's surface warms, and atoms and molecules leap free in a glittering exhale. That exhale glows. The color and timing of that glow carry clues. Sodium shouts in warm amber, magnesium flashes quick green, iron and nickel trace pale sparks, while simple gases freed from trapped ices add faint tints that fade as the fragment dives lower. It is a chemistry lab running at sprint speed, with the sky as the spectrometer and your pupils as the detector. Now meet the signatures. A fast, clean streak that turns on and off like a switch suggests a dense metallic speck that vaporizes briskly. A softer, fuzzy streak that brightens gradually can hint at a fragile, porous grain that crumbles as it goes. Some meteors leave persistent trains, ghostly threads that linger for minutes and twist in high winds. Those threads are not smoke as you know it. They are trails of excited atoms and molecules that react with the thin air. In that dance, sodium often paints an orange haze, while iron and magnesium leave pale ribbons that curl like tea steam. Watching how the train bends tells us the wind's aloft. Watching how the color fades tells us what was released and how quickly it calmed down. Prediction starts long before the glow. Streams of fragments trace the paths of parent bodies. For familiar meteor showers, we know the broad lanes. Interstellar fragments add a spicy wildcard. They come from directions that do not match the usual family roads, and they cruise faster than the regulars. That speed is not just drama. It changes everything about how bright and how high they flare. Higher speed means earlier ignition and thinner air, which preserves delicate chemistry for a blink longer. If a city network catches a dozen such streaks over a week from the same radiant point, odds are we are grazing a diffuse stream. The forecast folks take out their pencils. Tonight, before dawn, look east. The sky may mutter in brief syllables. How do we measure this without scaring off the poetry? With quiet tools that listen and watch. All sky cameras on rooftops stitch overlapping views into a wide dome, timing each streak to a fraction of a blink. Radio radar listens for head echoes, tiny reflections from the glowing plasma around a fragment, which reveals speed and size even through clouds. LiDARs pulse upward to read the drifting trains and extract wind maps at heights where no balloon floats. Infrasound microphones catch the soft thump of larger grazers that seed long glow trails. None of these instruments shout. They hum and send numbers, and those numbers feed models that learn which nights will fizz and which will yawn. Chemistry rides in the details. The ratio of early to late light, the depth at which a streak peaks, the presence or absence of a brief green flash. These combine into a profile. A stream rich in metal grains will spike fast and high, with narrow, crisp light curves. A stream laced with fragile ices will begin very high, glow softly, and often leave persistent trains that shimmy for minutes in the winds. If a cluster of events from one radiant shows uncommon sodium strength relative to magnesium and iron, you start to wonder about a parent that baked and then froze again, preserving salts near the surface. If another cluster shows stubborn neutral tones with few emission lines, you lean towards stony bits that have seen a lot of space weathering. No test tube, just the sky's own reveal. Now, layer the human side. Forecasting that feels like a friendly text. Imagine an app that treats meteors the way coastal towns treat tides. It knows your city's skyline, your local light habits, and the positions of streams expected to cross your patch of air. It combines last night's camera feeds, radar counts, and wind maps to say, in plain words, 7 minutes of alien snow at dawn, bring a thermos. You tap for details and see a simple arc where the radiant sits, a heat bar for likely intensity, and a palette for likely colors. No jargon, just a nudge to look up when the sky plans to whisper. The app is the tip of a quiet iceberg. Underneath sits a global core-up of sensors and people who agree to share. Schools run small cameras from gym roofs. Amateur radio fans lend their antennas for head echo listening. Weather services add high-altitude wind models. Observatory teams plug in fresh detections of fast movers that might seed grazers in a day or two. The result is a living map that learns. If a surprise puff hits one region, neighboring regions get a heads up for tomorrow morning. The sky writes a sentence. The network reads it aloud across time zones. What about real-time safety? Big fragments are rare, but the same system that delights can also warn. A fat, slow graze that will shed grit over a satellite highway triggers a quiet notice to rotate sensors or enter a safe pointing mode for a few minutes. The public never hears sirens. Operators get a gentle heads up, and work continues. Space weather and space traffic shake hands without drama. And yes, there is room for play. Pop-up gatherings form when the app flags a peak. Parks dim walkway lights. Cafes open early with warm bread and loaner blankets. And a local musician sets a soft rhythm as the sky scribbles above. The show is brief by design. That brevity is the charm. We do not command the sky. We court it. In the end, forecasting glow trails is not about guaranteeing wonder. It is about building a habit of attention. Tiny fragments tell truth in color and time. And if we listen well, we learn which visitor left which spice in the air. Next, we will hand that listening to students and citizens. turning the whole planet into a quiet observatory where a kid with a borrowed camera can help refine tomorrow's prediction before the bus arrives. Chapter 15: Education and Citizen Science. A classroom in the sky. Imagine homeroom beginning with a weather-style briefing, except the forecast is for meteors after lunch and a brisk chance of a faint visitor near the constellation that looks like an upside-down teapot. The bell rings, laptops open, and students are not memorizing constellations from a poster. They are pulling down last night's light curves and spectra from a shared archive and arguing, in the best way, about what the colors and timing mean. Science class becomes a newsroom with telescopes for cameras and graphs for headlines. Start with light curves, the heartbeat of moving dots. A light curve is simply brightness, measured again and again. In class, students learn to clean the data first. Remove the hot pixel that keeps yelling, correct for thin clouds that dull everything equally, and normalize the curve so it tells a story without static. Then the pattern hunt begins. A smooth rise and fall across minutes might mean rotation, as if the object is showing us bright and dark faces in turn. A sudden sharp spike could be a brief release of dust, like a sneeze in sunlight. 2 dimmings per cycle might hint at an elongated shape that flashes differently as it turns. Students sketch hypotheses on whiteboards and test them by folding the curve at candidate rotation periods to see if the peaks line up. There is a special kind of grin when the folds click and a messy line becomes a steady rhythm. Next, spectra. Instead of memorizing a chart of elements, students treat spectra like playlists. They learn to subtract the instrument's own signature, smooth without erasing delicate lines, and compare the cleaned rainbow to reference sets. That dip might belong to iron-bearing minerals. That gentle notch could be a whisper from water, ice shading the surface. That slope toward red might suggest space weathering that darkens and deepens hues. Teams build a short character sheet for the object, likely rocky or ice-rich, perhaps crusted with complex carbon stuff, maybe carrying grains so fine they behave like powder in moonlight. The point is not to win trivia. It is to learn to listen to numbers and ask good questions. Citizen science steps in as the scaffolding. Community observatories, backyard rigs, and school roof setups feed a cooperative pipeline where every contributor gets credit lines attached to the data they provide. A classroom with only a small scope can still play by confirming motion or capturing color pairs at specific times that fill gaps left by larger instruments. An elementary school can host an all-sky camera that catches fireball counts at night and uploads them at breakfast. Middle school coders help write the code that flags interesting events. High school art students turn last night's curve into an infographic that the whole town can read in one glance. A citizen network is not busy work. It is a lattice where each rung matters. Feedback loops make the learning real. When a class posts a cleaned light curve, they get a response from a mentor astronomer within a day. A note about a calibration tweak, a high five for catching a subtle feature, or an invitation to add their point to an official plot that will live in the object's public record. Seeing your lines stitched into a global figure is addictive in the best possible way. It says, this matters, and you made it better. Mentorship shifts from the old model of guest lectures to ongoing guilds. Universities adopt nearby schools and hold monthly data clinics where students bring their messiest curves and learn fix by fix. Observatory techs host streaming sessions from the control room so kids can watch a robotic mount slew and settle and understand why patience beats frantic clicking. Retired engineers teach the art of error bars, how to be honest about what you do not know yet, and why the courage to admit uncertainty is a superpower in science. Now the gleeful what if. Imagine a ready-to-launch microprobe sitting in a hangar, small enough to ride as a passenger on many rockets, and smart enough to take simple instructions from the ground. A global challenge opens each semester. Here is a newly found target, here are the constraints, propose a maneuver and an observation plan that fits the fuel, the timing, and the instrument limits. School teams form mission rooms, One group simulates trajectories, another drafts camera sequences, a third writes the communication script. Proposals arrive with crisp tables in plain language and a short video pitch. A panel of pros and peers selects a winner. The microprobe loads the plan, and during a real pass, it executes the student sequence. The data returns with the school's name in the header, extra credit for saving a satellite. Safety and ethics are baked in, not tacked on. Students learn that pointing a telescope is easy, pointing a narrative is harder. They practice writing objective observation notes that separate measurement from interpretation. They discuss why a small nudge of a harmless object might be okay in a drill and why a heavy hand is not. They role-play a data dispute and resolve it by comparing methods rather than volume. They keep chain of custody for their own samples from a meteorite kit, writing down who handled what and when. So the habit of careful record-keeping becomes muscle memory. Access is the engine. Not every school has a dark roof or a budget for a mount, so the network shares. Time on remote telescopes is scheduled like library books. A clouded-out night in one place becomes a clear window somewhere else, and the lesson goes on. A student with only a phone can still classify meteor videos by shape and timing, and those classifications feed the same pipeline as fancy spectra. Translation tools turn tutorials into many languages. The sky is big, the welcome should be bigger. The best part is the way this dissolves the wall between classroom and world. A quiet kid who loves spreadsheets becomes the hero when a gnarly calibration falls into place. A debate captain learns to listen to a faint signal instead of their own voice. A sports star catches the bug after a perfect meteor count under stadium lights left off for 1 hour by cooperative coaches. The ceiling of what counts in school lifts. By the time the final bell rings, a generation has learned that science is not a set of answers. It is a set of habits. Look carefully, clean your data, share your work, fix your mistakes, and tell the story straight. Tomorrow, when an alert pings before sunrise, some of those students will be the ones who catch the first frames. And the day after, they might be the ones who code the routing, schedule the scopes, and keep the whole orchestra in tune. Next, we will open the detective file, labeled Origins and Motion, using huge simulations to rewind the journeys of these travelers and find the nurseries and near misses that shaped them long before we looked up. Chapter 16, Simulating Origins, Rewinding Their Journey Across the Galaxy. Imagine dropping a handful of glitter into a slow whirlpool, filming it, and then running the video backward until all the sparkles gather where your fingers first opened. That is the spirit of simulating origins. We take today's positions and motions of stray visitors, wind back the cosmic clock inside a computer, and watch where the paths converge. It is less fortune-telling and more detective work with very patient physics. The cast of characters is big. There is the visitor itself, hurtling along with a particular speed and direction. There are the giant planets of our system that bend paths like courteous bouncers at the door. There is the sun, of course, setting the main stage, and then the larger neighborhood, passing stars that tug softly, clouds of gas that add tiny drifts, and the slow pull of the galaxy that leans on everything like a long breeze. The trick is to put them all into a digital model that remembers how gravity works, and then let time run backward, step by careful step, until patterns emerge. We begin with measurements. Every visitor promoted to a high-interest case gets its motion refined by many observatories, so the starting point is as crisp as possible. Then the simulator builds a moving star map, positions and speeds of nearby stars, over the last few million years, reconstructed from catalogues that track how those stars drift across the sky and toward or away from us. Sprinkle in the influence of spiral arm waves and the galaxy's gentle warp, and you have a stage that is not static but alive. Inside this stage, we release many clones of the visitor, each clone nudged slightly within the measurement uncertainties. Think of them as possible selves drawn from the same facts. We then press play in reverse. The clones fly outward from the present, weaving past planets and skimming by the orbits of neighbors, their paths braided like threads in a tapestry. Some threads loop past the sun cleanly and keep gliding. Others, when rolled back, show a near miss with a giant planet ages ago. The kind of event that could have launched the fragment into interstellar space in the first place if we were watching the forward film. This is where birth clusters enter the plot. Many stars are born together in loose swarms that slowly disperse like a party drifting into the street. Simulations include conserved fingerprints of those swarms, shared motions, and positions that still echo long after the nursery dissolved. When we run our clones back far enough, we do not just look for a single star. We look for these moving families. If several clones slide into the same group around the same time, our eyebrows rise. It is like finding the same hometown printed on a handful of luggage tags. Gravitational pinball adds texture to the story. In the forward direction, a fragment can be ejected from a newborn system by a close pass with a giant planet, or during a chaotic reshuffle when orbits are still settling. In reverse, that looks like a thread that approaches a star and then slides neatly into its disk, like a bead returning to a string. When many threads show similar returns to a particular system or cluster, our confidence grows that we have rewound to the right neighborhood. The model cannot guarantee the exact launch moment, but it can point at the street and say, "Look there." Simulations must also respect small nudges that add up. A tiny thermal push from sunlight on an irregular fragment can, over ages, shift a path by surprising amounts. We do not know that push perfectly for a given visitor, but the model can bracket possibilities. A gentle nudge this way, a gentle nudge that way. Run the film each time and see if a broad pattern survives. If all reasonable nudges still funnel the clones toward the same area, the result feels less like a fluke and more like a signature. Now the delicious what if. Suppose a season arrives when we detect not one, but several interstellar travelers within a few years, and their rewound threads, each with its own uncertainty cloud, overlap near the same nursery star. Different objects, different compositions, but matching stamps on different postcards. Perhaps the nursery was a lively place where giant planets played rough, tossing out debris during a brief, energetic era, or the cluster passed near a larger star, whose gravity jostled many small bodies at once, sending a flotilla into the wider dark. Either way, the model would whisper a compelling tale. You are not seeing random happenstance. You are seeing the echo of one youthful neighborhood's restless years. These rewinds are not just for origin stories. They also sharpen our forward predictions. By learning which past encounters with stars and planets mattered most, we can identify future waypoints where tiny measurements will pay huge dividends. A planned observation during a close pass by a certain star's path, for example, can collapse the uncertainty cloud for decades to come. Simulations become calendars with red circles. Observe here, learn a lot. The artistry of this work lies in uncertainty management. We do not pretend to know everything. Instead, we carry honest error bars through the entire rewind and summarize what remains, robust when you try many plausible worlds. Students of history know this feeling. You rarely get perfect records, but you can still reconstruct the march of events if multiple clues support the same arc. In our case, those clues are timing coincidences with star groups, consistent returns to certain galactic lanes, and families of solutions that refuse to wander off in random directions. There is also humility baked into the code. Sometimes the rewinds say, "We do not know yet." The clones fan out and never agree on a single birthplace. That is not failure. It is a request for better inputs. A few more nights of astrometry, a sharper measure of spin state, or a refined map of a passing star's past path can collapse the mess into a coherent braid. The universe loves to be coy. Simulations are how we learn to smile and ask better questions. Finally, there is joy. Watching a tangled set of lines gather into a graceful convergence, is oddly moving. It reminds us that chaos can produce memories, that the galaxy leaves footprints, and that perseverance can turn a mystery into a family reunion. With a handful of carefully rewound stories, we can tie the dust in our hands to the tantrums of distant baby worlds and the drift of their older cousins through the spiral arms. Next, we will pivot from families to oddities, opening the file of strange shapes, tricky spins, and surface quirks, cases where the usual rules do not fit neatly, and the whispers of design or unfamiliar physics tempt us to look twice before we shrug. Chapter 17. The Weird Case File. Shapes, Spins, and Whispers of Design. Open the drawer labeled Oddities, and you will find a museum of shapes that make engineers squint and artists grin. Some visitors look like pancakes stacked too thin for breakfast. Others resemble splinters so long and narrow, you wonder how they survived a single sneeze from a star. A few wear mirror-bright patches that flash like a signal, then go dull as if embarrassed. Welcome to the case file, where geometry, motion, and surface theater raise eyebrows, and occasionally the old question we pretend we have outgrown. First, shapes. Gravity usually prefers potatoes. Small bodies often relax into lumpy but reasonable forms, their rubble gently packed by time. And yet, every so often, we infer bodies that seem flattened like skipping stones or stretched like taffy. How could that happen? One path is gentle baking. In the deep cold, ices act like glues that can sublimate and refreeze, turning a porous chunk into a laminated slab. Another path is abrasion in slow motion. Countless micro-impacts sand away soft edges and leave a flat survivor, the way a bar of soap becomes a thin ellipse. Then there is the saga of tidal flexing. A close brush with a large planet can knead a weak object into a new silhouette. None of this requires intention. It only requires patience, which the universe stockpiles like canned soup. Now spins. Many visitors do not spin like tidy tops. They tumble, swapping axes as though they forgot the choreography. Tumbling tells you the object got shoved, not yesterday, but sometime in its past, by a collision, a thermal torque from uneven sunlight, or a gas jet that puffed at an awkward angle. The tumble rate can be a clue to structure. Fast, crisply repeating, bright and dark swings hint at a stiff interior. Slower, irregular swings suggest a pile of fragments held together by gentle cohesion, like a beanbag made of rocks. Watching the light rise and fall over several rotations, then fitting that rhythm with shape models, is how we sketch a three-dimensional guess with no tape measure and no ladder. Surface behavior is where the case file gets spicy. Some objects wear patches that throw tight flashes at just the right angles, implying smooth plates or fields of glassy grains laid out like a mirror that forgot it was in space. Natural, absolutely possible. Impact melt can cool into glass. Frost can sinter into slit crust. Even aligned crystals can act like tiny reflectors when the sun and our line of sight cooperate. But those neat flashes are irresistible hooks for speculation, because they read like a blink. Texture tells on a body's past mood swings. Rough, matte surfaces scatter light evenly, giving gentle curves in brightness. Smooth windows deliver sudden spikes. If those spikes repeat with unnerving regularity as the object turns, modelers take notice. Are we seeing facets from fracture planes that happen to be arranged just so? Or are we seeing a skin composed of plates that grew through freezing and thawing cycles, stacking like shingles on a roof? Either way, the surface is an autobiography written in glare. Dynamics add more whispers. A visitor that accelerates or decelerates slightly in ways not fully explained by outgassing can be a puzzle. Often the culprit is sunlight that heats one side more than the other, then re-radiates heat like tiny thrusters. Hollow pockets can amplify these effects. So can thin fins or ridges that act like sails for light, minuscule but persistent. We do not need secret engines to explain such nudges. we need careful accounting and a willingness to admit that tiny forces, applied for a very long time, are bullies. Observation bias deserves a chair at the table. Many wild claims are tamed once we remember that extreme light curves can come from extreme viewing geometries. If we watch a flat stone edge on, it looks fainter than a ghost. Then, half a spin later, it flares like a spotlight. A long shard twirling in just the wrong way can masquerade as a magic trick when it is merely a baton in a clumsy hand. The cure is patience and parallax, multiple nights, multiple angles, and, when possible, radar pings that help anchor size and shape instead of leaving us to guess from glints. Still, the file keeps one envelope labeled maybe. This is where patterns go when they are too tidy to ignore, but too sparse to indict. Imagine a surface that shows grooves or dots, whose spacing matches a prime number sequence within the uncertainty, not just once, but across several regions. Natural processes do love patterns. Crystals, fractures, ripples. But prime spacing is a fussy kind of order that materials do not stumble into often. If such a pattern held up under brutal scrutiny, we would not leap to grand stories. We would design new tests, higher resolution images to rule out tricks of shadow, spectra of the grooves to see if they differ from their neighbors, and thermal maps to check whether those regions heat and cool in ways consistent with machining or with quirky geology. Black holes are the universe's way of saying delete browsing history permanently. This would be the universe leaving a sticky note. Another whisper, balanced edges. Suppose an object shows a rim, so even that its silhouette barely wobbles over many spins. Could erosion carve a near-perfect ring? Yes, given enough time and a cooperative set of impacts. Could layered ices recede to a stable contour? Also yes. But the more perfect the edge, the more our eyebrows climb, and the more we beg for a close pass to settle the matter. The weird case file is not proof of designers. It is a magnet for better missions. Whatever the cause, the value of oddities is that they sharpen our tools. Strange spins force better shape models. Flashy patches demand improved calibration. Suspicious patterns teach us to separate genuine structure from the tricks of glare and timing. And if one day something refuses to be bullied by natural explanations, we will be ready to ask careful questions without blushing or shouting. Curiosity can be brave and polite at the same time. If all of this feels like a cliffhanger, good. The last chapter brings us home. We will step back from the microscope and the chase cams and ask what it does to a species to live in a port where strangers are expected, surprises are welcomed with a checklist, and humility is our dress code. Chapter 18, The Grand Reframe, From Solitude to Membership. Imagine our species as a lighthouse that once believed the sea was empty. The bulb was bright, the beam heroic, and the rocks well mapped. Then one evening, we saw distant lanterns sliding along the horizon, small and quick, and realized the shoreline is part of a wider harbor. That is the grand reframe. We are not a lonely island with a fancy flashlight. We are a busy port on a galactic inlet where travelers sometimes pass, sometimes wave, and sometimes drop a tiny parcel on our doorstep. The leap is not bravado. The leap is hospitality. Hospitality in space has nothing to do with mint pillows. It is a mindset that blends welcome with boundaries and curiosity with care. First, we greet. That means attention without panic, the way a good harbor pilot watches the water and reads the wind before lifting a finger. We built better eyes, we learned to listen, and we trained our reflexes until the first 10 minutes after hello became graceful instead of frantic. Then, we host. Hosting means catching the right details without making a mess, saying yes to questions and no to shortcuts, and remembering that every guest carries their own weather. Membership is the bigger word. A member shares the core list. In a cosmic neighborhood, that means keeping orbits tidy, telling neighbors when we plan a maneuver, and picking up after ourselves so the next traveler does not skate through our trash. It also means we share what we learn, A healthy port trades charts and stories. The shoals here are tricky. The currents there will fool you, and if you follow this line of stars, you will see dawn before you expect it. Our version of that is open data, honest methods, and the kind of credit culture that lets many hands lift a single discovery without anyone being crushed underneath. The old story said progress is leaving home. The new story says maturity is learning to live well where you are, even as you reach. What if the century's big leap is not the miles we travel, but the manners we practice? That sounds tame until you remember what manners are in science. Clear notebooks, clean rooms, transparent decisions, and instruments that do not pretend to be louder than the truth they collect. Good manners turn strangers into partners, and partners into a community that can do more than any lone hero with a loud horn. Humor has a job here. Jokes let us breathe while doing serious things. I like to think the cosmos enjoys a polite chuckle when our telescopes catch a shy visitor, and our first reaction is, "Scoot over, we saved you a seat in the data queue." Wit does not trivialize the stakes. It humanizes them. A smile travels faster than a press release. What changes when the port stays busy? Our default posture tilts from conquest to stewardship. We stop treating the sky like a trophy cabinet and start treating it like a library with rare books. You can read the pages, you can make a copy under soft light. You do not rip out leaflets because the paper feels nice. Stewardship is not a no, it is a yes, with a code of conduct, the kind that lets children and elders and visitors share the same room without stepping on each other's toes. It also reshapes ambition. We still dream of far journeys, but we understand that leaving a good house in order is part of the ticket. The port model asks us to invest in the unglamorous things that make everything else possible. Standards for time and position, public registries, rehearsal drills, and a culture that wears honesty as a uniform. None of this looks epic on a poster. All of it feels epic when it works, and the sky moves in step with us for a brief, shared performance. Membership invites new storytellers. The poem about a solitary astronaut becomes a chorus about the night shift at a hilltop observatory. The students who stitched their light curve into the global record. The technician who tightened the last seal on a vial that will sit on a shelf longer than any of us will hold our breath. The movie about a race to a comet becomes a quiet drama about a portable lab meeting, a returning capsule just above the air, the way customs meets a ship and asks gentle, important questions. Our heroes are still brave. They just carry lint rollers as well as flags. There is a moral shape to this too. A busy port teaches humility. We are not the measure of all motion. Visitors do not arrive to validate our myths. They arrive because gravity is redistributing its small change, because star nurseries are exuberant, because a giant planet somewhere shrugged at the right moment. We get to witness a few of those moments, and, if we behave, to learn from them. Humility is not a bow. It is a stance that keeps your footing when the dock rocks. So what do we promise the next generation? Not perfection, not an answer key. We promise good habits that turn surprises into lessons instead of messes. We promise tools that bend without breaking and rules that protect without suffocating. We promise that the door will be open to anyone who wants to help keep the harbor safe and interesting. Whether they write code, paint light curves, weld brackets, or sweep floors in a clean room where a teaspoon of dust can rewrite a chapter about how worlds begin. Here is the quiet thrill. If we keep this posture, the arrivals themselves will braid into a new kind of calendar. Years will be remembered by their guests. The season of the red-faced sprinter, the winter of the glittering slowpoke, the spring of the shard that told us about oceans under a shy sun. Our holidays will include nights when the city dims, parks open early, and small hands point upwards while older hands pour cocoa and say, "Watch." And then, yes, we will still go. We will build ships worthy of the wider sea, but when we go, we will carry the port with us, the habit of sharing, the rhythm of welcome, the reflex to clean up, and the grace to laugh when a plan meets the wind. The cosmos will remain enormous and unruly, We will remain small and persistent. That is a partnership worth tending.